Welcome to this explainer. Today we're actually digging into an 8th grade physics curriculum to break down what they call the mechanics of might. We're going to discover the literal formula that physically moves the universe. Seriously, have you ever wondered why some things are a total breeze to move while others feel, well, absolutely impossible? Today, we're unlocking those invisible rules of motion. Okay, let's just dive right into this really fascinating question. Think about it for a second. You could step outside right now, flick your leg, and send a soccer ball flying across a field, right? But getting a rocket off a launch pad, that requires millions of pounds of explosive thrust. So what's the fundamental difference there? Understanding this massive gap is going to unlock exactly how the physical world operates around us. Section 1. What exactly is Newton's second law?
So here's the absolute crucial point. Newton's second law elegantly boils down all the pushing and pulling in the entire world into a single, beautifully simple math equation. Force equals mass times acceleration, or as you've probably heard it, F equals ma. It essentially connects how heavy something is, how fast it speeds up, and how hard you actually have to push it, all wrapped up in one neat little package.
Now, to actually make this formula work, we've got to measure these 3 elements. In the physics world, force is measured in newtons, represented by a capital N. Mass is measured in kilograms, and acceleration, that's meters per second squared. Basically, when you push or pull an object, its acceleration depends entirely on just 2 things: how heavy it is, its mass, and how hard you push, the force.
Moving on to section 2, why F equals ma really matters.
This rule is literally the ultimate foundation for understanding how objects react when a force acts on them in our everyday lives. Like if you've ever helped a friend move, sliding a cardboard box full of pillows is a breeze. But a box packed to the brim with heavy textbooks, that takes some serious sweat-inducing effort. At the same time, if you drop a massive engine into a sports car, that extra force lets the car speed up or accelerate way faster than your average go-kart. And this brilliantly illustrates that without F equals ma, engineers simply couldn't build safe amusement park rides. They wouldn't even know how much force a roller coaster car needs to safely make it through a loop. And athletes, they wouldn't know how to optimize their running speed or exactly how much force they need to jump higher. This single principle connects classroom science directly to real-world problem solving across almost every major field you can think of. All right, section 3. How force works in action. Just think about pushing a shopping cart through a grocery store. When you first walk in, the cart is totally empty. It has very little mass, right? So a tiny push gets it rolling smoothly down the aisle. But by the time you hit the checkout, that same cart is loaded down with milk, canned goods, fruit. It has way more mass, which means if you want it to get it to accelerate at that same breezy speed as before, it's going to require significantly more force from you. If we scale this up step by step, you can see the relationship perfectly. A gentle tap applies a tiny force so a soccer ball barely moves. Give it a strong, powerful kick, that's much more force, so the ball accelerates quickly across the field. And then, bringing it all the way back to our very first question, rockets. A rocket has an absolutely colossal mass. Because it's so unbelievably heavy, massive engines have to produce an enormous sustained force just to lift it off the pad and accelerate it into orbit. Section 4. Let's check your knowledge. Okay, here's your first little challenge. Imagine you're pushing an object and the mass, the actual weight of it, stays exactly the same. What do you think happens to its acceleration if we push it twice as hard? Think back to that F equals ma formula. Yep, that's right. The acceleration doubles right along with it, because force and acceleration are directly proportional in that formula. If you apply twice the force to the exact same object, it is simply going to speed up twice as fast. Now, let's flip the scenario for question 2. What if the object suddenly gets twice as massive, twice as heavy, but you are still pushing it with the exact same amount of effort as before? What happens to the acceleration then? Exactly, the acceleration is cut in half. Because you're applying the exact same amount of force, that force naturally struggles to move a heavier object, which makes it accelerate much slower. A heavier object just naturally resists changes in its motion way more than a lighter one. Finally, section 5. Education, morality, and strength. So this specific curriculum we're looking at actually ties these physics concepts together with a verse from the Bible, Philippians 4:13. The text uses this to illustrate a core lesson for its students. Just as physical strength is required to move heavy objects in physics, the authors draw a parallel saying that God provides the spiritual strength needed to overcome life's biggest challenges. They're making the argument that both physical and spiritual realms require a foundational source of strength. The Academy's curriculum very intentionally intertwines biblical morality with its education. Their underlying philosophy here is that gaining raw knowledge without a moral compass can actually lead to negative outcomes. They basically compare it to a powerful rocket engine. If you have all that educational force, but absolutely no moral guidance system to steer it, the curriculum argues that power can easily become destructive. The lesson also draws on a promise from Romans, highlighting this idea that maintaining a spiritual mind brings peace. For the students engaging with this specific material, the stated goal is to experience peace of mind by keeping a spiritual perspective on their learning journey. It's about grounding their physics equations in something they see as deeper. As we wrap up this explainer, we're left with a really interesting philosophical question posed directly by the curriculum itself. Why gather all this brilliant scientific knowledge, like how the universe accelerates, if we aren't also building the moral framework to use it wisely? Whether you agree with their specific approach or not, it's definitely a fascinating look at how some educators combine scientific smarts with character building. Keep exploring, keep questioning, and we'll see you in the next explainer.